Acid, it's AP Physics C! Alright, ladies and gentlemen, we're going to be looking at this uniformly charged ring insulator with a charge Q, radius R, and it's like a three-dimensional drawing. So the ring is like in the YZ plane, and we're going to be looking at a point going through its center, which we're going to be considering the x-axis. And we're trying to find the electric field strength at this point perpendicularly out from the plane of the ring from its center. And I think I'm going to put the little E equals question mark on the top. Not that it matters. So once again, we're going to have to consider a little piece of the electric field strength due to a little piece of the charge. This charge right up here, dq. And if that's a little piece of positive charge, I know that right here at this point in consideration, there'll be a little piece of electric field going in this direction. We can call that dE. A little piece of the electric field. And of course what we need to do is find the total electric field strength. So the total electric field strength is going to equal the sum of all of the dE's. But these dE's are vector quantities. So if we look at the symmetry, we could see that all of the components in the y and in the z direction, guess what they're all going to do? They're going to cancel each other out. And in the end, what's the only thing that's going to end up adding up? The electric field strengths. Yeah, this is the easiest one. Exactly. I like how you're thinking. All the electric field strength in the x direction, they're the ones that are going to be added up. So if I break this dE up into parts and I say, well, look, this particular one here, there's dE in the x direction. And since I chose one right up on top, it would also have a piece going down in the y direction. I know that if I picked a point down here, it would have a component going upward in the y direction. And if I picked a point over here, it would have a component going in the negative z direction. And back here, it would have a component going in the positive z direction. But all of their dEx's would add up. So the dEy's and the dEz's cancel out. So in the end, all we need is the sum of all of the dEx's, the integral of those infinitely small dEx's. So if I assign this angle right here to be theta, this distance that the point is from the center plane there, we're going to call D. And up here we have the radius R. hypotenuse here, I'm going to call lowercase r at first. In a moment, we'll substitute something for that. But I could rewrite this now and say that this is going to be equal to dE cos theta, exactly. But dE here, you know what, maybe I should just write that first. I was going to skip this step. Glad you said that. dE times cos theta. Because if that's theta, that's theta. But what are we going to substitute in here for the dE? Well, that's just like this right here, guys. This is what we always go back to. Where are you? Come on. Right here. If you have a little piece of charge right there, and you're out here a certain distance r from it, we know the electric field strength due to a point charge is 1 over 4 pi epsilon 0 q1 over r squared. But instead of having a q1, the little piece that we're considering, we're calling dq. So it's just going to be dE is 1 over 4 pi epsilon 0 dq over r squared. Little r. What happened? What darnation? Hey! So, right here for this dE, I'm going to write 1 over 4 pi epsilon 0 times dq over this distance right here. The distance from dq to the point in consideration. And that distance is r squared. And the whole thing is going to be times good old cosine theta. Insert duplicate page. Back to this. So now I'm going to make some room here. Alright, so I'm just going to kind of, loop back now. So I got to make a substitution for this dq now. This dq right here. And, oh, you know what? This is the one case where I don't think we're going to have to make a substitution for dq. Because look at this. This here is going from 0 to q. And let's make some substitutions over here. So I could just say, oh, this is 0 to q, 1 over 4 pi epsilon 0 times dq. But what can I substitute in here for this r right here? Yeah, so, we know that this here is a squared plus b squared equals c squared, Pythagorean theorem. So this is going to be the square root of d squared plus r squared, where r is the actual radius of the ring. But then we're going to have to square it, so it's going to be d squared plus r squared. And then what about this cosine theta business right here? What can I substitute in for that? D over baby r, right? D over little r. But again, I don't want to leave it in terms of that, so it's going to be D over little r cosine theta. But instead of saying d over little r, I'm going to say d over the square root of d squared plus r squared. So that's going to be d over d squared plus r squared. And instead of saying square root, I'm going to say to the 1/2. So I can combine it with this guy here. That's a raised to the 1/2. So I could say 0 to q 1 over 4 pi epsilon 0 times d over, what do you get when you combine these two parentheses, when you multiply them? D squared plus r squared to the 3/2 dq. But this is not, this d here is not that d there, right? You know. Well, here's the thing, Tyler. Like, if you go around from this dq to the next dq next to it, to the next dq next to it, to the next dq, and you do it for all those different dq's, how does the r and the d compare for all of those dq's? They're all the same. They're all constants. Little d is always a constant. Little d is the distance from the center of the ring to the point in question.
Right, but I thought we don't, like, little d is not always the same distance away from the center, isn't it? Like depending on what the distance away is. Oh yeah, okay, yes, it's a constant, yeah.
Right, it's what distance we initially choose, and then once we initially choose a certain distance, but bam, that's staying the same. So d and r are always constants. So what can we say about all this stuff right here? They're constants. They can come out front. So basically it's just going to be equals 1 over 4 pi epsilon 0 times d over d squared plus r squared raised to the 3/2 integral of 0 to q dq. And if you go from 0 to q and you add up all the little dq's, what is that integral going to give you? Q. So the answer is just 1 over 4 pi epsilon 0 times d all over parentheses d squared plus r squared to the 3/2 times capital Q. Whoa. one.